Hello. So now we'll calculate the capacitance of a capacitor when the dielectric is placed inside the capacitor. So this is a dielectric, it is completely occupying the space within the capacitor. Okay, so this capacitor is having a free charge density sigma, and due to that free charge density sigma, there will be induced charge minus sigma will come onto the one side of the capacitor and the plus sigma will come onto the other side of the capacitor. Since it's a dielectric, then we already know that in case of dielectric, without the dielectric, the value of E naught, this E naught external field without dielectric, which is caused by the free charges, the value of E naught is sigma upon epsilon naught. And if you want to calculate it in terms of net charge, it will be Q upon A epsilon naught. That's the net field. That's the original field, external field. Now when this original field passes through the dielectric, then due to the dielectric, the polarizing fields come into the play, and which changes the value of net field, and the value of net field becomes E naught minus of E polarizing. And we also know that the value of E naught, E net, which is the field, net field inside the dielectric, is equals to the original field divided by the dielectric constant K. So this E net will become sigma upon K epsilon naught. This is the net electric field passing through the dielectric, and this dielectric is occupying the whole space. So this is the net electric field between the capacitor. And if you see this electric field, the value of electric field here is a constant. Since this value of electric field is a constant, so for constant electric field, we have a formula between the electric field and the potential difference between the plates. In this case, we'll calculate that. So that E is equals to delta V upon D, where this D is the distance between the plates. Since E is a constant, only when E is a constant we can utilize this formula. So in this formula, this delta V we have to calculate. Actually, this delta V is nothing but V max minus V minimum upon D. So we put the value of E, so it will become sigma upon K epsilon naught is equals to V by D, or in place of sigma we can write Q upon A epsilon naught K is V upon D, or we can say it will be Q by V is equals to A epsilon naught K by D. And if we compare with the standard equation of capacitance, so from standard equation, if you see, standard equation is Q by V is C. So if I compare with the standard equation, this C in this case becomes A epsilon naught K by D. Okay. So this is the net capacitance of a capacitor when the dielectric is placed inside the capacitor. And in this case, if you see, the earlier formula, when there was no dielectric, there was only air in between. Earlier formula was A epsilon naught upon D. There was only epsilon naught. And here the value of K being multiplied here. Or in this case we see this, since this epsilon naught times of K is nothing but epsilon, where epsilon is the permittivity of this dielectric material. So since this epsilon is the permittivity of this dielectric material, this formula we can write it as A epsilon upon D as well. So you see, this formula is same as the formula in case of previous case when the air was there. So this is like an original formula. In this formula, there is A is the dimension, cross-section area, D is the distance between the plate, and epsilon is the permittivity of the medium between the capacitor. If that medium is vacuum, we'll write the permittivity of vacuum, and if that medium is some dielectric, we'll write the permittivity of that dielectric, which we can also write as epsilon naught times of K. So this is the formula, but in this formula, you should remember that the dielectric is occupying the capacitor completely. There is no space basically. We have shown the space, but in reality that space is not there. Okay, so this is the formula and this is the derivation, and this formula we use to solve the equation to calculate the capacitance of the capacitors. Okay, thank you.